For today, we're going to take a look at section 3 dealing with cross product of two vectors. Now, the cross product is just another type of operation. Honestly, the book starts off, makes this more trouble than it's honestly worth. It makes it look way too hard. The idea is you have two vectors, u and v, and you take different components based on whether you're going to do I, j, or k of each of those values. So for the I, you don't ever use anything with a 1, 8, you just use the 2 and the 3. For the j, you don't use any of the 2's. For the k, you don't use any of the 3's. We've actually done something like this before, it just doesn't look like it. So if we rewrite it a little bit, so that rather than dealing with just the equations as they are, I just take the information from the equations, but you're actually just finding the determinant of a 3 by 3 matrix, where your top row is I, j, k. So if I take the I, j, and k, put those in the top row, then from u, I take each one of the coefficients. From v, I take each one of the coefficients, put into the rows. And then, remember doing this, find the determinant. You eliminate the row and column of that one value, and then do the determinant of what's left, times that I. Why is this minus here, though, for the j and then plus for the k? Anybody remember? Been a while, but it always alternates like that, where it's plus, minus, plus, minus, plus, minus, plus, minus, plus. As far as what signs, do you remember that? The minors and cofactor thing, kind of? Yeah, it has to do with that. But you can actually do this fairly quickly. So the idea, it has to be in linear combination form. So it has to be written with the I, J, K there. That's where that's coming from. In reality, though, you can just write I, J, K, and then component form for U, component form for V. Then find your determinant of that matrix using that top row. Your answer is your cross product. It generates a new vector. Now the reason we would want to do that is because that new vector has properties that we want to use. Okay. So just to review though, finding that for this u by v then, u cross with v. Well, I generate the matrix. The top row is always going to be that I, j, k. For u cross v, the next one's going to be the coefficients of u. So what am I going to put in for the next row? 2, 1, 3. For the bottom row, 1, 3, 2. Then I'm going to find the determinant of it. So what that means is I'm going to multiply diagonally. I'm going to eliminate this row, this column. So I'm just going to have what minus what? 2 minus 3, because you go in that direction, right? 2 minus, not 3, but 9. 1 times 2 minus 3 times 3. Remember that? Now that's going to be times I, and then it's always going to be minus whatever the determinant is for the j. It should be that. So what's going to go inside with the j? 4 minus 3. So if I cover up this row, diagonal minus, downward diagonal minus the upward diagonal. And then plus or minus? Plus. Only one that's minus is that middle one. Yeah, 6 minus 1. So the result you get is just negative 7 I minus 1j plus 5k. That's your cross product. It generates a new vector from those previous two vectors. Whereas if you're doing dot product, what's your answer look like? Single number. Okay? So what's going to be the difference if I do v cross with u? Yeah, you're going to flip the rows, right? So I still have I, j, k, but now it's going to be 1, 3, 2 and 2, 1, 3. So when I do that, what am I going to get for a determinant? What's happening? Yeah, you're flipping the signs. Because these positions are just swapping here. The diagonals are essentially switching places. So you have 9 minus 2, you have 3 and 4, and you have 1 minus 6. Okay? So when I do that, that's going to give me the same as this, just what's different? Signs. So I have 7i plus j minus 5k. What's going to happen if I do v cross with v? So v cross with itself. Yeah. No, because when I minus this, I'm going to get 3 minus 4, so it's going to be a negative here. So it is a negative of negative, so it cancels out. But all that happens here is all the signs switch from the solution. What do you get? 0. Yeah, 0. Because if I do that matrix here, I'm still going to have the ijk, and then I'm going to have 1, 3, 2, 1, 3, 2. Right? So every time you do a diagonal, you're going to get something minus itself. So 2 minus 2, or 6 minus 6, or 3 minus 3. So you're just going to end up with the 0 vector. In other words, the origin. That'll happen anytime you cross something with itself. You generate the origin. Does that make sense? Okay. So you got some basic properties that arise because of this. There we go. The one we talked about where the signs, if you flip the order, the sign switches. If you're crossing, when you're adding two vectors together, the distributive property applies. If you're multiplying a scalar multiplier, though, you either want to do it first to the first one or to the second one, or wait and do it to the final vector. It was the word I was looking for. But you don't want to do it to both vectors. You only want to apply it to one, either one before or the one final answer you get. If you dot something with 0, of course, it's going to turn into, or cross something with 0, it's going to turn into 0. Cross something with itself, you also get 0. And then it doesn't matter if you actually dot one of the vectors with the cross product or cross product two of them and then dot them, you're going to get that same result. Okay. Now, could I do cross vectors twice with 3 vectors? Could I have u cross with v cross with w? Potentially you could. Because you're just going to get a vector and then cross it again. But can I dot a vector, 3 vectors together? No, because one of them turns into a single number. So as soon as you cross 2 of them together, you get a single number times a vector. Okay. And now, some of the properties we're actually going to utilize for this. Come on. Gotta get used to that. You can't slide it up because it runs into this. Okay, so if you cross them, and this is one of the main places we'll use this, if you cross 2 vectors together, the result is orthogonal to both of the original 2 vectors. What's orthogonal mean again?
Perpendicular.
Perpendicular, but it's a little more than that. It's actually the fact that if I think about the x-axis and the y-axis, so if I were to draw x-axis and y-axis, and I were to actually cross those together, I would generate this z-axis. Because it's perpendicular to, or orthogonal to both of those. It's actually orthogonal to the plane. That's what ends up happening. Whatever plane is formed by those 2 vectors that you're crossing, you generate, when you cross them, when you do that cross product, you generate a vector that's orthogonal to that plane created. So a lot of times you actually end up describing things using that. If I cross 2 vectors together and take their magnitude, that's actually going to be the same thing as if I did the magnitude of each individually and multiplied by sine of theta. The angle between the 2 vectors, the 2 original vectors. Lastly, if I do the cross product of the magnitude of the cross product, that's also going to be equal to the area of a parallelogram, where those are 2 of the sides. That's where this one comes from as well. That's another formula for the area of a parallelogram. But this, the nice thing about this one is I don't need to know theta. So as long as you have a vector form of 2 sides that are touching each other for a parallelogram, you can figure out the area of that parallelogram. Without needing to know heights, without needing to know angles, anything. Okay, so if I have these 2 vectors and I want to generate a unit vector that's orthogonal to both of them. So if I just want a vector that's orthogonal, what do I do? Yeah, cross them together. Tell you what the whole section's about. So if I do the cross product, what do I do first? Yeah, that matrix, top row is IJK. Middle row? 2, 3, negative 4. Bottom row? Negative 1, 2, 0. So, what do I end up with in front of the I?
0 minus 6. 8, sorry.
Okay, cover up this one. 0 minus negative 8 is 8. So I get 8i. And then plus or minus? Minus, because it's going to be j. And what do I get there? Oops, sorry. So when I subtract that, I'm going to get negative 4. So it's going to be minus negative 4, which will turn into plus 4. Okay. There's a lot of sign flipping there, so be careful. What about for k?
4 minus 3.
So 7. Okay. So that's an orthogonal vector, but I need the unit form of it. How do I find the unit form of that vector? Divide by the magnitude. So to find the magnitude of this vector, that's going to be the square root of what? So 8 squared is plus, giving you 129. Okay, so when I go to write this, I'm going to generate the vector. That's 8 over that square root of 129. Oops, or 192, 129. Times I plus 4 over square root of 129. Keep writing 19 for some reason. J. And then 7 over square root of 129. I did that 3 in a row. What the heck? Talking faster than I'm writing. 7 over the square root of 129. Okay. Thing over.
The pointed brackets.
You can write it either way. This is linear combination form. And the only reason I'm doing this all the way through is because that's the way this works with the IJK as the top row. But if you put it in component form, that's fine too. Which would just be none of the letters and commas and arrow brackets. The same thing. Yeah?
How can you even get rid of the negative?
It's minus negative. When I do the determinant for j, it's 0 minus 4, right?
Okay. Thanks.
Yeah, that negative is flipping a lot, so it is easy to lose track of why it's there, but yeah.
That negative sign's hard to see. It looks like you just kind of like put a little thing. The negative sign.
Better?
Sure.
No, it doesn't.
Anyway. Show that the quadrilateral with vertices given is a parallelogram. Honestly, as weird as it sounds, it does again help to start by graphing. Okay? So if I do a rough sketch of this thing, and yes, you can do a rough sketch in 3-space. So 3, 5, 0. I'm going to go out 3 over 5, not up or down at all. 1, 2, 4, out 1, 2, up 4. 1, 3, 4, out 1 again, over a little farther, and up 4. And for D, out 3 over 6. By doing it that way, you can pretty easily tell where the quadrilateral is. Okay? You end up with this weird slanted something or other. The question is that a parallelogram? Well, what are the properties of a parallelogram? Opposite sides are parallel. They are also. They're also what? Congruent. They're the same length. Okay? So, I just need to show that they're equal and congruent.
I wasn't wrong.
Well, they are straight, yes. So, what I need to do is actually generate some of these. I'm going to turn them into vectors just so I can work with them that way. So what vectors does it look like are parallel up here? AD and BC. So if I turn those into vectors, what's the vector for AD going to be? So, well, it's A2D, so it'd be 0, 1, 0. Take D minus the A, right? BC? Yeah, subtract C minus B, again, 0, 1, 0. So what does that tell me if I get the exact same vector? That means they're parallel. Because if I took them and repositioned them so they both start at the origin, they would actually be the same line. Because they're going out the same exact distance, there's not even a multiplier, that tells me they're also congruent. So these are parallel and congruent. What about the other two sides? What would those be? So CD and BA. CD is what? 2, 3, negative 4. And 2, 3, negative 4. So again, parallel and congruent. That's enough for the first part. They're both parallel and congruent. That means it's a parallelogram. How would I go about finding the area of this parallelogram? Magnitude of what? Yeah, magnitude of their cross product, right? So you actually want to multiply these, cross these together. Now, if I did these two, though, would that accomplish anything?
No.
No, that's just going to give me 0. So make sure you do the ones, the sides that are adjacent to each other. So A to D and C to D. So when I do that, the magnitude of AD crossed with CD. Well, first off, I got to go through that whole process again. But the nice thing is, you're working with 0, 1, 0, right? So, good.
Can you use like XYZ? 5JK?
The problem then it's not considered to be written in linear combination form. You could, whatever's there, just as long as you realize that that's giving you the x, y, and z value for a component. Okay, and that you throw out the pluses. You got to make sure you're turning it into that combination form or component form. That's fine. Just it doesn't naturally flow from one step to the next, so it can throw people sometimes. Although often what happens is they just screw up signs, but you miss points because of it. So what do you end up with? So if I jump straight to component form, the nice thing is with all these zeros, oh wait, -4, right?
Yeah.
He used this row by accident. So what do you get for the middle one? 0. For the last? Okay. Now. Yeah. One thing to watch out for. Which one of those could potentially be incorrect if there wouldn't have been a 0 there?
The middle one, subtract.
Yeah, you got to make sure you flip whatever result you get on the determinant. Now, because it's 0, it doesn't matter. But if it was some other number, make sure you flip the sign because it should be -j. That's why I often don't go straight to this. It's because that negative sign gets screwed up. So then what ends up underneath the radical for the magnitude? Yeah, you have 16 plus nothing plus 4, so you get the square root of 20. That would be your area of this parallelogram. So rather than finding the height and all that stuff, I can just use those two sides. Does that make sense? Yeah, you probably should. And yeah, actually, if you want to be technical, you should also have square units on there too.
Do take off if we don't label it.
Depends. Honestly, if they don't give you units to start with, I usually don't bother. If they say feet, then I would like to see square feet there,
Okay.
that kind of thing. Am I done?
Yes.
No. Is it a rectangle? How do I test for whether it's a rectangle or not?
Angle?
What about the angle?
It has to be 90 degrees.
So I can actually be even lazier. I don't actually need to find it. I just need to prove whether it's 90 or not.
Yeah.
What can I do to prove whether it's 90 or not? Without finding the angle. What? Dot product. What's the dot product tell me? What? If they're orthogonal or not. Well, if they're orthogonal to each other, then their dot product is what? 0. So find the dot product. Again, do I want to do the dot product of these two? No. So those are across from each other. I want to do the ones that are adjacent to each other. So I'm going to do the dot product of AD and CD again. So that's going to give me what? So in other words, 3. So since AD dotted with CD is not 0, then not a rectangle. Make sense? Okay. I'm going to stop there for today, let you guys work a little bit. Monday, we're going to do the last part of this section. And let's see. Tuesday, we'll look at section 10.6. Wednesday and Thursday, we'll look at 11.4. That's the last section of the chapter. Friday, you don't have school. Okay. So the test will be the week after that.